On a warm night in 1977, a small Ohio radio telescope recorded 72 seconds of noise no scientist has ever fully explained. 2 days later, a volunteer astronomer named Jerry Eman was paging through printouts when he found something impossible. He circled it in red ink and wrote one word beside it: "Wow." The signal arrived from the direction of Sagittarius at nearly the exact frequency two physicists once predicted an alien transmission would use. Big Ear caught it once, then never again. Not that week, not that year, not in the 49 years since, despite dozens of searches with instruments far more sensitive than the one that found it first. Tonight, we sit with the most carefully studied unexplained signal in the search for company in the dark. If tonight's mystery stays with you, consider liking this video and subscribing quietly, the way you'd nod to an old friend, because that small gesture is what keeps stories like this one coming your way. Settle back now and let your evening slow down. In 3, 2, 1, liftoff. For most of human history, the night sky has been something people looked at, not something they expected to hear from. The stars simply hung there, silent points of light, more backdrop than conversation. By the middle of the 20th century, though, a small number of scientists had begun taking seriously an idea that would have sounded like pure fantasy only a generation earlier, that somewhere among those countless points of light, another civilization might exist, and that civilization might, just possibly, be trying to say something. Turning that idea into an actual research program meant building an instrument willing to listen patiently, for years at a stretch, to frequencies almost nobody else thought twice about. Few instruments built for that purpose were ever stranger or more effective than the one that stood on a wide stretch of farmland north of Columbus, Ohio. A machine built to do exactly one thing waited there: listen. It could not swivel toward an interesting star, the way the telescopes in the movies always seem to. It had no motor built to chase a comet across the sky or follow a passing spacecraft. It simply lay open to the heavens, fixed in place, and let the turning of the earth itself carry the entire universe slowly past its face, one narrow strip of sky at a time, night after night, for decades. The people who built it gave it a plain, almost affectionate nickname, Big Ear, and on a warm night in 1977, it caught something that no one has ever been able to fully explain since. Big Ear did not look like the sleek dish antennas most people picture when they hear the words radio telescope. It was flat, enormous, and strange, a rectangle of wire mesh roughly 340 feet long and 70 feet wide, tilted toward the sky like the page of a book propped open against the horizon. Beside it stood a second reflector, curved and standing upright, that gathered the faint radio waves bouncing off the flat one and focused them down into a pair of receivers mounted nearby. Laid out together on the ground, the whole structure covered enough farmland to be compared, more than once, to 3 football fields set end to end, out past the edge of a small college town where cornfields still ran right up to the property line. It had been designed by a radio astronomer named John Krause, a professor at Ohio State University known for building enormous, resourceful instruments out of comparatively modest budgets. Rather than pouring money into a single steerable dish, Krause had found a cheaper, cleverer way to gather the same amount of sky. Spread flat across the ground, the way it was, the whole arrangement collected radio waves over an area equal to a traditional dish, roughly 174 feet across, a size that would have cost a fortune to build the conventional way, achieved instead with wire mesh, steel supports, and a great deal of careful engineering. By the time it switched on in 1963, it was already one of the largest radio telescopes anywhere on the planet, hiding its scale in plain sight behind a design so unusual that a passerby driving past on the county road might easily have mistaken it for farm equipment. For its first decade of operation, Big Ear had a very different job than the one that would eventually make it famous. Between 1965 and 1972, it carried out what became known as the Ohio Sky Survey, methodically cataloging nearly 20,000 radio sources scattered across the heavens, faint galaxies, and quasars that had never been recorded in any catalog before that patient stretch of work began. It was careful, unglamorous work, the kind that rarely makes headlines but quietly fills the reference books that other scientists spend entire careers building on. Page after page of coordinates and measurements that would outlast the instrument that gathered them. By the early 1970s, though, the survey was essentially complete, and Krauss and his small team faced a question every observatory eventually faces once its original purpose has run its course. What do you point a great, expensive instrument at next? Krauss already had an answer in mind, and it was a stranger one than counting radio galaxies. He had grown fascinated over the years with a much larger question: whether anyone else out there, on some world circling some other star, might be listening back. In December of 1973, Big Ear was formally repurposed for a continuous search for extraterrestrial intelligence, becoming one of the first observatories anywhere to treat that search not as a brief experiment squeezed between other projects, but as an ongoing, dedicated program. It would go on to run longer than any other search of its kind ever conducted, a persistence later recognized in the Guinness Book of World Records. Dedication did not pay the electric bill, though. Not long after the search began in earnest, the National Science Foundation, which had helped fund Big Ear's earlier survey work, shifted its support toward larger national facilities and away from smaller, university-run observatories like this one. The money that had once kept a paid staff on site quietly dried up year by year until it was mostly gone. What kept Big Ear listening after that was not a grant or a government contract. It was a small, devoted circle of volunteers, engineers, professors, and local science enthusiasts who drove out to the observatory on their own time because they believed the search was worth doing whether or not anyone was paying them to do it. The telescope itself sat on land belonging to Ohio Wesleyan University, sharing its grounds with the older, more traditional Perkins Observatory nearby, so that visitors coming to look through a conventional dome telescope on any given evening might glance across the field and see, almost as an afterthought, the strange flat structure quietly listening for something no ordinary telescope could ever see at all. Among them was a physicist named Jerry Emmon, who had earned his doctorate at the University of Michigan and had been drawn into Krauss's orbit back in the late 1960s, splitting his professional life between teaching and this quieter, unpaid work of scanning the sky for something that, by any honest accounting, might never come at all. By 1977, Emmon had been part of the observatory's tight little community for roughly a decade, long enough to know the rhythms of the place better than almost anyone, and long enough to have grown comfortable with a kind of patience that most people never have to learn. The work itself had almost nothing dramatic about it, at least not on the surface. A steerable telescope, one that could chase a single target across the whole sky, would have let the team choose exactly where to look, but it would also have cost far more than the observatory could ever hope to raise. Krauss's fixed design traded that flexibility for something just as valuable in a search meant to run for years: total, unbroken coverage of an entire strip of sky, swept past the beam automatically, every single day, without anyone having to decide where to point it. Not far from the reflectors themselves, stood a small, unremarkable building where the real work happened, housing the receivers, the on-site computer, and the printer that turned raw readings into something a human being could actually sit down and read. Big Ear's receivers stayed tuned to a narrow band of frequencies clustered around 1420 MHz, a choice made for very deliberate reasons that will matter enormously to this story before it is finished. As the Earth turned, each strip of sky drifted through the telescope's fixed beam for a little over a minute at a time, first crossing one receiving horn, and then, a few minutes later, crossing a second horn mounted just beside it, so that any genuine signal from a fixed point among the stars would, in principle, be caught twice, once in each horn, as a kind of built-in confirmation. The receiver split that narrow band into 50 separate channels and checked each one every 10 seconds for anything unusual, feeding the readings into an on-site computer that translated them into a code simple enough to print on paper. An ordinary background reading came out as a low single digit. Anything stronger climbed upward through the numbers, and if it climbed high enough, it spilled over into letters, so that a truly powerful signal might read not as a 9, but as a letter climbing steadily toward the top of the alphabet. Day after day, the machine listened without complaint, and day after day, a dot matrix printer somewhere nearby chattered out long, accordion-folded sheets of paper covered in columns of numbers that mostly said, in their own quiet way, the same thing over and over: nothing here, nothing here, nothing here. Someone had to read all of it, and that job fell to the volunteers, who took turns showing up to work through the backlog. It was every bit as tedious as it sounds. The printouts arrived in thick, folded stacks nearly as heavy as a small city's phone book, dense columns of single-digit numbers running down page after page, and a volunteer would settle in with a cup of coffee and a red pen, running their eyes down each column looking for anything that broke the pattern. Most shifts turned up nothing at all worth marking. Occasionally, a page held a stretch of numbers slightly higher than the baseline around it, and nearly every time, that bump traced back to a known radio source, a distant galaxy already catalogued years earlier during the Ohio Sky Survey, drifting harmlessly back through the beam exactly where it was expected to be. It was patient, humbling work, the kind that asks a person to show up again and again for a payoff that, statistically speaking, might never arrive in their lifetime or in anyone's. Eamon was simply one of the people who kept showing up anyway, week after week, because somebody had to, and because he wanted to be the one reading the page on the day it finally mattered. Nobody at the observatory talked about the odds out loud very often. There was no need to. Everyone who volunteered there already understood, in the way people understand the rules of a game they have chosen to keep playing, that the search might easily outlast all of them without ever producing a single confirmed result, and that showing up anyway was simply what the work required. On the night that would eventually change how an entire field understood its own search, Eamon was not even at the observatory. Big Ear required no one standing over it once it was running. It simply recorded whatever drifted through its beam and let the printer keep its own pace, sometimes for days at a stretch, until a volunteer arrived to change the paper and gather up what had accumulated. That particular August night, with the cornfields around the observatory settling into the last warm stretch of summer and the stars coming out one by one over the flat Ohio horizon, the machine spent its usual quiet hours sweeping across a narrow band low in the southern sky, in the direction of the constellation Sagittarius, recording channel after channel of ordinary static exactly as it had 10,000 times before. No one stood beside it, watching. No light came on to mark the moment. The reflector simply held its position, the way it always did, while the Earth turned beneath a sky that, for 72 seconds, was about to stop behaving like every other night before it. Nothing about that particular patch of sky had ever drawn any special notice from anyone. It was simply the next strip in line, the way every strip of sky eventually became the next strip in line, on a machine that never slept, never hurried, and never played favorites among the stars. It was built to hear. 2 days later, on August 17th, a fresh stack of printouts was waiting when Eamon sat down to work through the backlog, the way he had done so many times before that the motion barely required conscious thought anymore. He moved through it the same unhurried way anyone develops for a repetitive task, letting his eyes travel down each column almost automatically, the endless low numbers blurring into something close to a rhythm of their own, page after page of 1s and 2s and 3s, drifting along the baseline, exactly where they belonged. Every so often, a slightly higher run would catch his eye, and every time, a quick check confirmed it against a source already sitting comfortably in the observatory's own catalogue. One more familiar galaxy, passing back through the beam, right on schedule. Page after page passed beneath his pen without a single mark worth making. And then, partway through the stack, something on the page simply refused to behave. Where every other line held single digits drifting quietly near the baseline, one run of characters climbed sharply upward, held near its peak for a moment, and then eased back down again, tracing a shape unlike anything else on the page. 6EQUJ5. To anyone unfamiliar with the observatory's simple intensity code, that string would have looked like almost nothing, a stray sequence of letters and numbers easy enough to glance past without a second thought. The code itself was nothing more complicated than a way of squeezing a lot of information into a small space, readings from 0 up through 9 for anything ordinary, and then for anything stronger than plain background noise could account for. The scale simply kept counting upward into the alphabet, letter by letter, so a volunteer could tell at a glance, just from the shape of the character, whether a given 10-second sample was routine or remarkable. To Eamon, trained to read exactly this kind of printout for the better part of a decade, it meant something very specific and very hard to ignore. The reading climbed from an unremarkable 6 through the ordinary numbers, and then kept climbing straight past them into the letters reserved for signals, far stronger than anything ordinary background, noise, or routine interference ever produced, all the way up to the letter U, a reading representing something on the order of 30 times the noise floor around it. In a career spent reading pages that almost never said anything at all, this page was practically shouting. Before he did anything else, he checked the surrounding pages, the way any careful reader would, looking for some ordinary explanation waiting just out of sight. No storm had been logged that night. No equipment failure had been noted. The channel on either side of the reading sat exactly where it should have, flat and undisturbed, which meant whatever had happened cleanly, in one channel only, exactly the way a genuine signal from somewhere far off would be expected to behave. He did not call anyone right away, and he did not, by his own account afterward, pause to consider the full enormity of what he might be looking at. He simply circled the 6 characters in red ink, the same pen he kept on hand for marking anything worth a second look, and in the narrow margin beside them, without stopping to choose a more dignified word, he wrote the only thing that came to mind in that moment. Wow, it didn't take long, he would later say, for him to recognize that this was extremely interesting, and whatever else the observatory's years of quiet, unpaid searching would or would not eventually produce, this single circled word, scrawled in the margin of a printout, would go on to become the thing the entire project was remembered for, long after almost everything else about it had faded from public memory. What made that particular reading worth circling was never simply that it was strong. Strong readings, taken alone, are common enough in radio work. A nearby thunderstorm, a passing aircraft, a loose connection somewhere in the equipment on the ground. Any of these can send a needle briefly into the red without meaning very much at all. What held Eamon's attention was the specific shape of the signal and everything that shape seemed to imply. A passing aircraft or a piece of ground equipment cycling on and off tends to leave a rough, irregular mark on a printout like this one, jumping up and down unevenly, sometimes cutting off in the middle of a reading with no warning at all. The numbers Eamon was looking at did nothing of the sort. They rose gradually across several 10-second samples, reached a single clean peak, and eased back down again in an almost symmetrical curve, tracing almost exactly the shape you would expect from a fixed point somewhere out among the stars, drifting slowly through a stationary telescope's narrow field of view as the Earth itself turned beneath it. That rise and fall, stretched across a window of just about 72 seconds from beginning to end, did not look like the signature of something happening nearby on the ground. It looked like the signature of something very far away, holding perfectly still, while an entire planet quietly rotated underneath the dish, listening for it. 72 seconds was not a coincidence, either, and it would take a little explaining later on for anyone outside the observatory to appreciate exactly why. Because Big Ear could not turn to track anything, every signal it was ever capable of recording had exactly the same maximum possible duration. The amount of time it took a single point in the sky to cross the width of the telescope's fixed beam as the planet's own rotation carried it past. For a source sitting where this one appeared to sit, low along the summer horizon, that window worked out to just about 72 seconds, not a second more. The reading had used every bit of the time available to it, arriving right as the beam picked it up and fading right as the beam released it again, exactly the way a genuine, fixed point of radio energy among the stars would behave, and nothing at all like the sudden, ragged bursts that ordinary local interference tends to produce. The reading had also appeared on only a single one of the receiver's 50 channels, a slice of the radio spectrum so narrow that almost nothing found naturally out in space is capable of producing it cleanly. Stars, gas clouds, and most of the other ordinary objects scattered across the night sky tend to radiate across a broad smear of frequencies at once, closer to how sunlight spreads across every color at once than to a single, pure musical note. What Eamon found on the page behaved nothing like that. It stayed confined, almost stubbornly, to a narrow sliver of the dial, no wider than a fraction of a single one of the receiver's 50 channels, clustered close to that same 1420 megahertz mark. The entire search had been built around from the very beginning. A signal that narrow takes a great deal of effort to produce. Nature tends toward the broad and the messy. Concentrating that much energy into so thin a sliver of frequency is the kind of thing a deliberately built transmitter does, not the kind of thing a cloud of gas or a distant star typically does on its own. A narrow, oddly clean spike arriving from a fixed point in the sky, lasting exactly as long as the physics of the telescope said it should, centered almost precisely on the one frequency this particular observatory had spent years specifically built to hear. Whatever it turned out to be, it plainly was not ordinary background noise, and everyone who examined that printout in the days and weeks that followed understood as much almost immediately. Word traveled quickly once Eamon shared what he had found. In the unhurried way word traveled, in the years before anything could move faster than a letter or a phone call, Krauss, the observatory's founder, looked over the reading himself, and in the months that followed, interest in the discovery reached well past the small circle of volunteers who kept Big Ear running day to day. Even Carl Sagan, already among the most recognizable scientists in the country by the late 1970s, wrote in to ask for more detail, and Krauss wrote back, describing exactly what the printout showed and exactly what it did not. The field these letters passed through was still a small one in 1977, a scattering of observatories and university departments where researchers mostly knew one another by name, so that a genuinely strong candidate signal, even an unrepeated one, was the kind of news that reached nearly everyone working in the search within a matter of months rather than years. Inside the small, close-knit world of observatories searching for artificial signals from other worlds, a community that measured its victories in decades rather than headlines, the story of one tired, careful volunteer, circling 6 characters in red ink and writing a single word beside them, spread almost as far and as fast as any story reasonably could, in an era when a discovery still had to travel the old way. One conversation at a time. The name stuck immediately, and it stuck for a reason worth pausing on. Scientific discoveries are rarely handed names as plain and human as this one turned out to be. There was no formal designation waiting in line to be assigned, no committee gathered to debate a proper title. There was only the word a careful, unhurried man had written in the margin of a printout because it was the truest thing he could think to say in that particular moment, and somehow, against every ordinary rule of how these things are supposed to work, that word turned out to be exactly the right one. Decades later, it remains the only name most people have ever needed. But even in that very first week, one detail refused to sit comfortably alongside everything else. Big Ear's design used not one receiving horn but 2, mounted so that a single point in the sky would drift first through the beam of one horn and then, a few minutes later, drift through the beam of the second, tracing what should have been the same signal twice, as a kind of built-in confirmation that whatever had been recorded truly belonged to a fixed point among the stars and not to some passing fluke on the ground. It worked the way a second witness works in any careful investigation. The first horn's reading was a single account of what had happened, useful but not yet proven, and the second horn's reading was supposed to be the corroboration that turned an account into a fact. For a source sitting where this one appeared to sit, that second detection should have arrived almost exactly 3 minutes after the first, a clean, expected echo confirming everything the first horn had already shown. It never came. The first horn recorded the signal in full, rising and falling exactly the way it should have. The second horn, sweeping across precisely the same coordinates a few minutes later, recorded nothing at all. Not a fainter version of the same reading. Not even a hint of one. Simply silence, sitting exactly where a plain, tidy confirmation was supposed to be waiting. It was a small thing to notice on a page otherwise filled with a single, circled triumph, and in the excitement of that first week, it would have been easy enough to set aside for later. It did not go away that easily, though, and it would go on quietly troubling nearly everyone who examined the case in the years that followed, long after the celebration of that first discovery had settled into something more patient and far more difficult, the slow, careful work of trying to understand exactly what had been caught that August, and why, out of every night Big Ear had ever spent listening, it had chosen to answer, however briefly, on this particular one. For now, in that first week, what they had was a printout, a red circle, and a word in the margin, along with a puzzle about a second horn that had stayed stubbornly silent when it should not have. It was not proof of anything. It was not, on its own, even a complete scientific case. It was a single, extraordinary data point, sitting alone, with no way yet to know whether it would ever be joined by another. what none of them could have fully explained yet, not even Eamon himself, as he sat there turning the printout over in his hands, was why 1420 MHz mattered so much to begin with. Out of every frequency available across the entire radio spectrum, the search had not settled on that particular number by accident, or for convenience, or because it happened to be an easy part of the dial to build a receiver for. It had been chosen years earlier, for reasons rooted deep in the physical nature of the universe itself, laid out in a proposal that two physicists had published in a scientific journal long before Big Ear was ever built, back when the whole idea of listening for another civilization still sounded, to most people, like something out of a novel rather than a serious research program. That reasoning is where this story turns next, because understanding exactly why this one signal happened to look so much like precisely what an entire generation of scientists had spent years hoping to find is the only way to understand why, 49 years later, no one connected to it has ever quite been able to let it go. The reasoning traced back to 1959, nearly 2 decades before Eamon ever sat down with that printout, to a puzzle two physicists had set for themselves at Cornell University. Giuseppe Cocconi and Philip Morrison were not in the business of chasing aliens. They spent their careers on particle physics, the kind of work that fills chalkboards with numbers rather than headlines. Morrison, in particular, had already lived through one of the most consequential chapters in the history of physics, having worked years earlier on the Manhattan Project, and had spent much of his later career thinking hard about what science owed the wider world once a discovery left the laboratory. But somewhere in their reading, they had stumbled onto a question so simple it was almost embarrassing that no one seemed to have worked through it properly before. If another civilization, somewhere out among the stars, ever wanted to signal across the emptiness between two solar systems, and if we ever wanted to listen for it, how would either side know where on the radio dial to even begin? It is a harder question than it first sounds. Radio waves span an enormous range of frequencies, from the low end used for ordinary broadcast radio all the way up past what any household receiver could ever tune to, and a civilization broadcasting on the wrong one might as well be shouting into a canyon while the person listening stands in a completely different valley. There was no shared history between any two civilizations separated by dozens or hundreds of light years, no prior conversation to fall back on, no way to send a letter ahead of time proposing a channel. Whatever frequency either side chose would have to be one both sides could arrive at independently, using nothing but the same universe both of them were staring up into. Cocconi and Morrison went looking for a physical constant, something built into the fabric of the cosmos itself, rather than into the habits of any one culture, and they found their answer in the most common substance in all of creation. Hydrogen is everywhere. It is the simplest atom that exists, a single proton with a single electron circling it, and it makes up the overwhelming majority of ordinary matter in the universe, filling the vast clouds that drift between stars, fueling the furnaces at the heart of every star that has ever burned, including the one this planet orbits. Look up at almost any of the glowing nebulas that fill astronomy photographs, the great pillars and clouds where new stars are still being born, and what is glowing is, more often than not, hydrogen gas, lit from within by the young stars forming inside it. It is the raw material every galaxy is built from, the first element to exist at all, formed within minutes of the beginning of the universe itself, long before the first star ever gathered enough of it together to ignite. Scientists estimate that hydrogen accounts for somewhere around 90% of all the atoms in existence, a proportion so overwhelming that nearly everything else in the periodic table, every trace of carbon, oxygen, iron, and gold, amounts to something closer to an afterthought by comparison. No matter which galaxy a civilization happened to call home, no matter how different its sky looked from ours, hydrogen would already be woven through everything that civilization had ever studied, long before it built its first radio telescope. Deep inside every one of those countless hydrogen atoms, every so often, the electron performs a tiny flip, reversing its spin, and in doing so releases the faintest possible whisper of radio energy, always at precisely the same pitch on the dial. Multiply that whisper by the almost unimaginable number of hydrogen atoms scattered across a single galaxy, let alone the universe beyond it, and the whisper becomes a hum steady enough for any radio telescope on any world to detect, a signature written into the sky by physics itself rather than by any particular species. That was the insight Kokkoni and Morrison published in a scientific journal called Nature, and it amounted to something like this: any civilization advanced enough to build a radio telescope would, sooner or later, point that telescope at the sky and notice hydrogen's quiet hum, glowing at the same fixed frequency every other such civilization would eventually notice too. It would not matter what star that civilization circled, what language it spoke, or how differently its history had unfolded from our own. The physics of a hydrogen atom does not change from one solar system to the next. There was a second piece to their reasoning, one that mattered just as much as choosing the right address on the dial. If a civilization ever wanted to be heard across a distance measured in light years, simply broadcasting would not be nearly enough. A radio signal, like anything else, loses strength as it spreads outward, the same way a candle looks brilliant up close and vanishingly faint from across a field. Spreading a message thin across a wide range of frequencies, the way an ordinary light bulb throws its light out in every direction, would scatter whatever power was available so thoroughly that almost nothing would survive the crossing. Concentrating every bit of that same power into one narrow, precise sliver of the dial, the way a beam of focused light stays bright over far greater distances than a bulb ever could, was the only realistic way to make a signal loud enough to survive a journey of that length. A narrowband transmission was not simply a curiosity. It was the obvious engineering choice for anyone serious about being heard, which is exactly why theorists had long predicted that a genuine signal, if one ever arrived, would be found squeezed into an unusually thin slice of the spectrum rather than smeared broadly across it. Researchers in the field would later come to call this kind of evidence a technosignature, a trace left behind not by any natural process but by deliberate engineering, and a narrow, artificial-looking spike sitting on top of nature's own broad hydrogen hum was, by that standard, about as clean a technosignature as anyone had ever theorized. Think of two ships, hopelessly out of contact with one another, adrift on the same dark ocean with no way to radio ahead and agree on a meeting point. Left to their own devices, both captains would likely steer toward the same lighthouse, not because they had coordinated in advance, but because it was the one landmark bright enough and common enough that either of them could be reasonably certain the other would notice it too. Hydrogen's frequency was exactly that kind of lighthouse, visible from anywhere, agreed upon by no one, and yet somehow already shared by everyone capable of looking for it. In 1959, this was still a genuinely strange thing for two respected physicists to put their names to. The serious scientific community mostly treated the search for other civilizations as a pleasant enough thought experiment for a dinner party, not the subject of a peer-reviewed paper, and a career built on particle physics was not, on the surface, the safest place from which to propose that humanity start listening for aliens. Cocconi and Morrison were careful about how they framed it, presenting their idea not as a prediction that anyone was actually out there, but as a straightforward calculation of where a search ought to begin if the question was ever going to be answered honestly, one way or the other. That framing mattered. It let other scientists engage with the proposal as a piece of sound reasoning about probability and physics, rather than as idle speculation, and it is a large part of why the paper survived contact with a skeptical scientific establishment instead of being dismissed outright. Cocconi and Morrison closed their proposal with a line that would go on to outlive almost everything else they ever published, a quiet acknowledgement that the odds of success were impossible to calculate in advance, but that the odds of success without ever trying were exactly zero. It was less a scientific claim than a dare, aimed at whichever radio astronomer might be willing to take it seriously enough to actually point an instrument at the sky and listen. Someone did, within a year. A young astronomer named Frank Drake, working at the National Radio Astronomy Observatory in Green Bank, West Virginia, built what may have been the first deliberate search of its kind. A modest project he named Ozma, after the storybook queen of a faraway, imaginary land. Using an 85-foot dish, Drake spent several weeks in 1960 listening to two nearby, sun-like stars, hoping to catch some trace of exactly the kind of hydrogen line transmission Cocconi and Morrison had described. He heard nothing that first attempt, no beacon, no message, nothing beyond the ordinary hiss of the cosmos. But the search itself had proven something worth proving. It was possible, with existing equipment and a reasonable amount of patience, to actually look, and looking, however briefly, turned a thought experiment into a legitimate branch of astronomy. The following year, Drake gathered a small group of researchers to think through, systematically, just how many civilizations capable of sending such a signal might realistically exist, breaking the question down into a chain of separate factors, from the rate at which stars form to the fraction of those stars that might host a planet capable of supporting a technological society. The resulting framework, later known simply as the Drake equation, offered no firm answer, since half its terms were pure guesswork in 1961 and remain closer to guesswork even now, but it gave the entire search something it had never had before: a disciplined, honest way of asking how big a task this really was, instead of simply hoping. Drake's approach and the approach Big Ear would later take were, in a sense, opposite strategies aimed at the same target. Ozma had chosen two specific, promising stars and listened to each of them closely, the way a person might focus every bit of attention on two doors they had good reason to believe someone might eventually walk through. Big Ear, once it joined the search more than a decade later, took the opposite gamble, choosing not to guess which particular star might be worth watching, and instead letting the sky itself decide, sweeping methodically across whatever happened to drift past its fixed beam each day, trusting that patience and thoroughness might succeed where careful selection could not. Neither approach was more correct than the other. They were two honest answers to the same impossible problem. Nobody yet knew where to look, so the field, sensibly, tried looking in more than one way at once. Over the following decade, the idea kept growing, and in 1971, an engineer named Bernard Oliver helped lead a NASA-funded summer study that pushed Cocconi and Morrison's original reasoning a step further. Oliver noticed that hydrogen was not the only common molecule with a distinctive radio signature. A little further up the dial sat the hydroxyl radical, a fragment of a water molecule scattered thinly throughout space, singing out its own faint, reliable note. Between those two markers, hydrogen at one end and hydroxyl at the other, sat a quiet, relatively interference-free stretch of the radio spectrum, and Oliver gave that stretch a name that has outlived nearly everything else written in his original report. He called it the water hole, because hydrogen and hydroxyl together make up water itself, and because a water hole, out in open country, has always been the place where creatures who share nothing else in common still find themselves gathering side by side, predator and prey alike, lowering their guard for a few minutes at the one spot the whole landscape can be trusted to provide. It was a small, warm piece of poetry, sitting inside an otherwise dry engineering study, and it stuck for the same reason the word wow would stick nearly 6 years later. It captured something true in language anyone could hold on to. Oliver's report went further still, arguing that this stretch of the dial deserved to be protected from ordinary radio traffic the same way a real water hole might be fenced off from careless development, on the reasoning that a civilization patient enough to keep it clear was a civilization signaling its own seriousness about being found. The idea spread quickly through the small community of researchers already thinking seriously about the search. Within a few years, nearly every deliberate search for artificial signals then underway, whatever equipment it used and whatever institution funded it, had settled on some version of the same targeted stretch of spectrum, less because anyone had proven it correct beyond doubt, and more because no one had proposed anything more convincing since. It became less a hypothesis under active debate and more a working assumption the whole field simply built on top of. The way a town grows up naturally around the one reliable well, rather than scattering itself randomly across the surrounding countryside. This was the tradition Big Ear had been built to continue. When Krauss and his volunteers pointed their receivers at that narrow band clustered around 1420 MHz, they were not making an arbitrary engineering choice out of convenience. They were placing a very specific, very deliberate bet, staked on more than a decade of careful reasoning by physicists and engineers who had never met each other's colleagues, working years apart, arriving independently at the same conclusion: that if anyone out there was going to be found, the water hole was the most sensible place in the entire radio spectrum to start listening. Every design decision that went into the receiver, the width of each of its 50 channels, the sensitivity it needed to catch something faint, the decision to log a reading every 10 seconds rather than less often, traced back to this same body of reasoning about what a genuine signal would need to look like in order to be caught at all. Big Ear had spent years patiently watching that narrow stretch of the dial, waiting for something to pass through it that did not belong to the ordinary hum of hydrogen alone. And then, on an August night in 1977, something did. What makes the signal M encircled so difficult to dismiss is not simply that it was strong, or that it behaved like something fixed among the stars, rather than something happening on the ground. It is that it appeared almost exactly where an entire international tradition of careful, skeptical reasoning had spent nearly 2 decades insisting the most promising signal would appear if one ever came at all. Cocconi and Morrison had never seen Big Ear's printouts. Oliver had never met Eamon. None of them could have known, when they wrote their reports, that a plain rectangle of wire mesh in a cornfield outside Delaware, Ohio, would one day catch something matching their reasoning so closely. The theory had been built first, in the abstract, from nothing but physics and careful thought. The signal arrived years later, seemingly answering a question that had been asked in exactly the right language, at exactly the right address, without any way of knowing in advance that anyone would ever be listening from that particular cornfield on that particular night. No single piece of evidence, taken alone, would have carried much weight. A strong reading happens occasionally on any sensitive instrument, a narrow signal can, in rare circumstances, arise naturally. A source that behaves as though it is fixed among the stars might, in principle, be explained some other way, given enough imagination. What made this case different was that every one of those individually unremarkable details lined up at once, in the same 72 seconds, on the same page, at the one specific frequency. 2 decades of careful theorizing had already marked as the most sensible place to look. Coincidences of that size do happen in science, occasionally, and no honest researcher will ever claim otherwise. They simply do not happen often, and when they do, they tend to earn exactly the kind of scrutiny this one received. Researchers in this field have long relied on a careful ladder of language to describe exactly how much confidence a given piece of evidence deserves, running from a confirmed observation, meaning something measured directly and beyond reasonable dispute, down through a strong interpretation grounded in that measurement, and further still into a candidate explanation, one plausible account among possibly several, before finally reaching pure speculation, an idea worth considering, but resting on little more than imagination. What Eamon had recorded belonged, without question, to that first and sturdiest category. The reading itself, its strength, its shape, its narrow width, its frequency, was a confirmed observation, verified and re-verified against the raw data. Everything built on top of that observation, every explanation for where it might have come from, would have to be judged far more cautiously, and it is that second, far more difficult question that would occupy the search for decades to come. A discovery that tidy demands a healthy amount of suspicion before anyone gets to celebrate it, and in the weeks that followed, that is exactly what it received. Long before anyone allowed themselves to entertain the more remarkable explanations, the team worked through the mundane ones, the way any careful investigation has to, in roughly the order any careful investigator would choose. Start close to home, and only move farther away once every nearby possibility has been exhausted. Aircraft were an obvious early suspect. A plane broadcasting on a nearby frequency, however unlikely at exactly that slice of the dial, could in principle leave a strong mark on a printout, but aircraft interference tends to behave erratically, drifting and fading unevenly as the plane itself moves. Nothing like the smooth, clean rise and fall Big Ear had recorded from a source that behaved as though it were fixed among the stars rather than crossing the sky under its own power. Military and government transmissions came next on the list, if only because a classified or restricted signal, however unlikely, would at least explain why something so precise and so powerful had never been publicly logged anywhere else. That possibility, too, failed to hold up. Nothing about the reading's behavior matched the kind of transmission a ground-based military system would produce, and the frequency itself sat inside a portion of the radio spectrum that international agreement had already set aside specifically to protect it from exactly this kind of interference. That protection was not incidental, and it says something about how seriously the waterhole had already been taken by the time Big Ear caught its signal. By the 1970s, the frequency surrounding the hydrogen line had been formally recognized through international radio regulations as a band reserved for scientific listening, off-limits to ordinary broadcasters and transmitters, precisely because so much of what radio astronomy cared about, from mapping hydrogen clouds across the galaxy to searching for exactly the kind of signal Big Ear was built to catch, depended on that stretch of the dial staying as quiet as possible. Governments that had never spoken to one another about searching for other civilizations had, all the same, agreed to keep this one particular corner of the spectrum clear for reasons that had nothing to do with aliens and everything to do with basic astronomy. It made the frequency doubly unlikely as a source of ordinary interference, and doubly interesting as the address where something extraordinary had chosen, however briefly, to show up. Satellites came under the same scrutiny next. Dozens of artificial objects were already circling the planet by 1977, some of them broadcasting on frequencies uncomfortably close to the hydrogen line, and each one had to be checked against its known position that night and ruled out in turn, none of them lining up with the timing or the direction of what had actually been recorded. A satellite crossing the sky brings its own kind of telltale signature too, since an object moving quickly relative to the ground tends to have its transmission stretched or compressed slightly as it approaches and recedes, a subtle shift in pitch along the way. Nothing of that kind showed up in the reading Eamon had circled. It is worth pausing on how thoroughly this possibility was chased down, precisely because it is the explanation any reasonably skeptical person reaches for first. A satellite passing overhead was, on paper, the simplest and least remarkable answer available. It was also the answer the evidence refused to support, once anyone actually sat down and checked the numbers against it. Ground-based interference took longer to eliminate, if only because there were so many possible sources to consider: a piece of nearby equipment with a loose connection, a stray transmission from a nearby installation, even mundane household electronics from the surrounding farms, any of which might occasionally spike a receiver this sensitive. Each of these possibilities shared a common weakness. Once examined closely, nearly all local interference arrives briefly and then vanishes, or repeats itself unpredictably as whatever machine is causing it cycles on and off. And none of it typically confines itself with such discipline to a single 10 kHz sliver of the dial, while leaving every neighboring channel completely undisturbed. The observatory's own equipment was checked as carefully as anything else on the list, since the least dramatic explanation of all would simply have been a fault somewhere in Big Ear's own receivers, a loose cable, or a stray electrical surge dressed up to look like something more than it was. The equipment checked out clean, then and in every later inspection. Nothing on the ground, examined honestly and without the benefit of wanting a more exciting answer, behaved the way this particular signal had behaved. No equipment malfunction was ever logged at the observatory that matched the timing. No known aircraft, no known satellite, no known transmitter anywhere in the vicinity accounted for it. None of this happened in a single afternoon. Ruling out an entire category of possible explanation properly takes weeks of correspondence, cross-checking records that were not always easy to obtain, and simply waiting for the right piece of information to arrive in the mail from somewhere else. One by one, the ordinary explanations fell away, not because anyone wanted them to, but because none of them actually fit the evidence sitting on the page. What remained, once the mundane possibilities had been set aside, was a signal that matched theory with an almost uncomfortable degree of precision and a history of terrestrial explanation that had, quite simply, come up empty. That combination is what turned a single circled reading into something the entire search for extraterrestrial intelligence would spend the better part of the next 50 years unable to set aside. It was not proof. Nobody serious ever claimed that it was. But it was, by the standards the field itself had spent 2 decades carefully building, about as close to the ideal candidate as anyone had any right to expect. Science, though, does not generally accept a single instance of anything as settled, no matter how well it matches expectation. A single observation, however striking, is a starting point, not a conclusion. This is not a standard invented specifically for the search for other civilizations. It is the same standard that governs any claim in any field, from a new particle glimpsed once in a collider to a new medicine that seems to work in a single early trial, an event that cannot be repeated. However carefully it was recorded the first time, remains a promising lead rather than an established fact. The entire discipline of radio astronomy runs on the assumption that a real, ongoing phenomenon out among the stars should, at least occasionally, be willing to show itself again, especially to an instrument built specifically to notice it. If the source responsible for that 72 seconds of narrowband energy was still out there, sitting at the same coordinates, doing whatever it had been doing on the night it was first recorded, there should have been no shortage of opportunities to catch it a second time. Big Ear was still listening, night after night, exactly as it always had. It would simply need to be pointed, deliberately and repeatedly, back at that same small patch of sky near Sagittarius, and given the chance to prove that what happened once could happen again. That is precisely what came next, and it is where this story turns from a single remarkable night into something far longer and far more demanding. The slow, patient work of waiting for a moment that had happened once to happen again, using instruments that would grow more sophisticated with each passing year, aimed at a target that, for reasons no one could yet explain, seemed to have no intention of cooperating. Whatever had passed through Big Ear's beam that August night, whether it turned out to be the beginning of an answer or simply the most convincing false alarm in the history of the search, it had already done something no theory alone could ever manage. It had proven, at least once, that the waterhole was worth watching. Eamon did not wait long to start looking again. In the weeks after that August reading, he and the rest of the small team at the observatory pointed Big Ear back at the same patch of sky near Sagittarius again and again, hoping simply to catch an echo of what had already been recorded once. It was, in practice, the same unglamorous routine that had defined the search from the very beginning. The same stacks of printouts, the same red pen, the same long hours spent scanning columns of numbers that almost always said nothing at all, except now, every session carried a different weight than it once had. Where a volunteer had once hoped, in a general and mostly abstract way, that something interesting might eventually turn up, everyone reviewing those particular pages now knew exactly what they were hoping to see again, down to the shape of the reading and the 6 characters it would spell out if it ever returned. Nothing came. Not that autumn, not that winter, not in any of the repeated attempts that followed over the next several months. The silence was not, on its own, unusual. A search built around patience had always understood that most nights would produce nothing, and one quiet stretch, however disappointing, proved very little by itself. But as the weeks turned into years, and the same coordinates kept returning the same flat, uneventful readings every time anyone thought to check them, that silence began to take on a shape of its own, less like an absence and more like a standing question nobody could quite close the book on. Word of the reading had already reached well beyond the observatory's own small circle by then, and as magazine articles and, later, television programs picked up the story over the years that followed, the pressure to either confirm or dismiss it only grew, even as the actual evidence available to work with stayed exactly the same as it had been from the very first printout. Big Ear kept working long after that first excitement faded from the news. The volunteers who had kept the observatory running through the lean years of the 1970s stayed with it through the 1980s and into the 1990s, still splitting their time between paying jobs and unpaid nights spent scanning printouts, still finding nothing that matched what had been recorded that one August evening. The formal search finally came to a close in December of 1997, after roughly 24 years of continuous listening, longer than any search of its kind had ever run before or has run since. Big Ear itself did not last much longer. In 1998, the land it stood on was sold, and the telescope that had once been counted among the largest radio observatories on the planet was dismantled to make way for an expansion of a nearby golf course. The great flat reflector, the curved standing dish, the small building that had once housed the receivers, and the chattering printer, all of it came down within the year, sold for scrap or simply hauled away, the way a barn or a grain silo gets cleared once the land underneath it becomes worth more than the structure ever was. Where a flat rectangle of wire mesh had spent 35 years listening patiently toward the stars, there is, today, a stretch of manicured fairway, and golfers walking that particular course have, for the most part, no reason to know what once stood beneath their feet, patiently aimed at the same stretch of sky, night after night, waiting for an answer that never came a second time. The story of how one gave way to the other is, in its own quiet way, as much a part of this account as anything recorded on a printout, a reminder that even the instruments built to ask humanity's largest questions remain, in the end, ordinary property, subject to the same balance sheets and real estate decisions as anything else, standing on a piece of land somebody eventually decides to sell. The search itself did not end with Big Ear, even if that particular instrument's part in it did. Other radio telescopes, considerably more sensitive than the one that had made the original discovery, took their own turns listening to that same stretch of sky whenever their schedules allowed it, over the years and then the decades that followed, part of a broader search that grew steadily more capable, even as the specific mystery it kept circling back to refuse to budge. Arrays of dishes working in concert, computing power that would have been unimaginable to anyone reading a printout in 1977, and search programs backed by far larger budgets than Big Ear's volunteers had ever enjoyed. All eventually took a turn pointed at that same small stretch of Sagittarius. None of them ever found anything resembling a repeat. The signal remained exactly what it had been from the very beginning, a single, unrepeated 72 seconds, recorded once, on one night, by one instrument, and never again by any instrument since, no matter how much more capable those later instruments became. That fact alone, more than any single piece of technical analysis, is what kept the case alive for so long. A repeated signal invites confirmation or explanation. A signal that only ever happened once invites something closer to permanent, low-grade wonder, the kind that never quite resolves itself, but never quite goes away either. Two separate efforts ran alongside each other from that point forward, related but not quite the same. One was the search for a repeat, the patient, ongoing work of pointing ever more capable instruments back at the same coordinates and hoping. The other, quieter but in some ways more demanding, was the work of trying to explain the original recording itself, using only the evidence that already existed, without any guarantee that new data would ever arrive to help. The first effort, decade after decade, kept coming up empty. The second produced, over time, a small handful of genuine candidates, each one worth taking seriously, each one eventually tested against the same unforgiving standard. Does it actually match everything Big Ear recorded that night? Not just the parts that are convenient to explain. Into that open space, over the years, came a series of proposed explanations, each one taken seriously enough to test, and each one, so far, falling short of settling the question for good. Some reached for the mundane, hoping ordinary chemistry might account for what an extraordinary printout seemed to suggest. Others reached for a specific point of light in the sky, hoping a single well-chosen star might finally give the case an address. One reached deep into the archives of an instrument that no longer exists, hoping better analysis of old data might succeed where new observations never had. And one, arriving only very recently, reached for the strangest coincidence the story has produced yet: a visitor from beyond the solar system passing through at an angle that seemed, on paper, almost too convenient to ignore. None of them, so far, has closed the case. Each deserves to be told honestly, in the order they actually happened, with exactly as much confidence as the evidence for each one has actually earned. The first explanation to draw real public attention arrived nearly 40 years after the original discovery, in 2016, when an astronomer named Antonio Paris proposed that the signal might have come not from anything remotely artificial, but from a pair of comets that happened to be passing through roughly the right part of the sky at roughly the right time. Comets, as they near the Sun, shed enormous, loosely bound clouds of gas, including hydrogen, stretched out behind them by the pressure of sunlight and the solar wind, into structures that can span millions of miles. Paris identified two comets, one called 266P, Christensen, and the other, a smaller, less familiar object, known simply as Gibbs, and argued that neither had been catalogued yet back in 1977, meaning nobody checking the sky that August would have had any way of knowing either comet was even there. To test the idea, Paris did not simply propose it and move on. Working with a small telescope of his own, he waited for both comets to pass back through roughly the same part of the sky years later and measured their actual hydrogen output directly, comparing what he recorded against the strength of the original 1977 reading, publishing his results and inviting other astronomers to check his work against the archived data for themselves. It was an appealing idea, in part because it offered something the story had never quite had before: an explanation requiring nothing stranger than ordinary chemistry, no artificial transmitter, no unresolved mystery. Just two icy visitors from the outer solar system drifting past at an inconvenient moment. It also did not hold up well once other researchers examined it closely. Comets shedding hydrogen produce a broad, diffuse glow rather than the narrow, tightly focused spike Big Ear had actually recorded, nothing like the disciplined, hydrogen line precise signature that had made the original reading so remarkable in the first place. Astronomers who reviewed Paris's own measurements pointed out that the hydrogen signal he had recorded from the comets directly was far too faint by a wide margin to account for a reading as strong as the one Eamon had circled, meaning that even setting aside every other objection, the comets simply were not bright enough at that frequency to have been responsible. The timing created its own problem too. Big Ear's design meant that any genuinely fixed point in the sky should have swept through both of its receiving horns a few minutes apart, and while that particular anomaly had never been resolved for the original signal either way, a comet, moving steadily along its own orbit rather than holding still among the fixed stars, would have produced a noticeably different pattern across the following nights as its position continued to shift, a pattern nobody was ever able to find in the historical record. Eamon himself, by then long retired from active research, but still following the case closely, was blunt about his skepticism. "We do not believe the two comets theory can explain the wow signal," he said, and the wider community of radio astronomers who examined the claim largely agreed with him. The comet hypothesis remains, at best, a candidate explanation that failed its own test, a reminder of how easily a tidy answer can seem to fit until someone checks it carefully against the evidence. The next serious attempt came several years later, in 2020, and took a different approach entirely. Rather than trying to explain the signal away with something already known to be passing through, an independent researcher named Alberto Caballero set out to identify what might actually have been sitting at the far end of that beam, fixed and waiting, on the night Big Ear was listening. Working through a large public catalogue of nearby stars, compiled from a European space mission that had spent years precisely mapping the positions and properties of more than 1 billion stars across the galaxy, Caballero narrowed his search to the specific stretch of sky the signal had come from and worked through dozens of candidates, checking each one's temperature, size, and brightness against our own suns, looking for anything close enough to a genuine match that a planet in its orbit might plausibly have had the billions of years needed to develop the kind of civilization capable of building a radio transmitter. He found one strong candidate, a sun-like star roughly 1,800 light-years away, sitting almost exactly where the signal appeared to have originated. For the first time since 1977, the case had something it had never quite had before, not just a frequency and a direction, but an actual, specific star that a telescope could be pointed at directly. Astronomers working with the Breakthrough Listen project, a large, well-funded modern search for exactly this kind of techno-signature, took the candidate seriously enough to do just that, aiming a sensitive radio telescope directly at the star and listening carefully across a wide range of frequencies, including the one that had mattered so much in 1977. The instrument they used was, by any measure, a different order of machine than Big Ear had ever been, capable of detecting signals many times fainter than anything the original fixed telescope could have picked up, watching not just the waterhole itself, but a far broader stretch of surrounding spectrum at the same time. If that star, or anything near it, had been broadcasting on any regularly recurring basis, even faintly, this was about as thorough a listen as the technology of the time could offer. They found nothing. No narrowband spike, no hydrogen line transmission, no trace of anything resembling what Big Ear had once recorded, coming from that star or from its immediate surroundings. The candidate star was not thereby proven meaningless. It remains, today, an entirely reasonable place to have looked, sitting close to where the original signal seemed to originate, and matching the physical profile theory had long predicted a hospitable star should have. But a specific, targeted search, using an instrument considerably more capable than Big Ear ever was, had come up empty, and that result was enough to move the star from promising candidate to, most likely, simply an interesting star that happened to sit in the right direction, with no detectable connection to the signal at all. It was, in its own way, a useful result, even in its disappointment, narrowing the field of remaining possibilities by one more name, and leaving the case exactly as open as it had been before anyone thought to check. For a time after that, the search settled into something closer to its old rhythm, patient and largely uneventful, the kind of quiet stretch the field had grown accustomed to over the decades. Then, beginning in 2024, a research team working under an astrobiologist named Abel Mendez, based at a planetary habitability laboratory associated with the university that operates the Arecibo Observatory in Puerto Rico, took a different approach still. Rather than searching for a repeat directly, they went back into archive data the Arecibo telescope itself had already collected years earlier, sweeping broadly across large sections of the sky, and asked a narrower question. Had anything resembling the WOW signal's specific signature ever shown up elsewhere in data, nobody had gotten around to examining that closely. It had, though never anything quite as dramatic as the original. Scattered through the archive, the team found a handful of fainter, similar-looking narrowband spikes, each one traceable back to known, cold clouds of hydrogen gas drifting quietly through the galaxy. The same kind of hydrogen that fills the vast nurseries where new stars are born. On their own, cold hydrogen clouds like these do not typically produce anything bright enough for a telescope on Earth to notice, sitting quietly and drifting for millions of years without ever calling attention to themselves. But the team proposed that something occasionally lights them up from behind, some sudden, energetic flash arriving from far outside the cloud itself, most likely from a magnetar, the collapsed, city-sized core of a once massive star, wrapped in a magnetic field far stronger than anything else found anywhere in nature, or possibly from a related, briefly furious class of object called a soft gamma repeater. Only a couple dozen magnetars have ever been confirmed anywhere in the galaxy, scattered remnants of the rare, especially massive stars whose deaths left behind not an ordinary dead star but this stranger, far more volatile kind of object, prone to sudden outbursts that can, for a brief moment, outshine almost anything else in the sky at the wavelengths they favor. Both kinds of object are capable of releasing, in a fraction of a second, more energy than most ordinary stars release in years, and either one, positioned just beyond a cold hydrogen cloud and firing off one of its rare, violent outbursts, could conceivably illuminate that cloud from behind the way a sudden flash of lightning briefly lights up a bank of fog from within. A burst of energy from an object like that, passing through a cold hydrogen cloud at just the right angle, could in principle trigger every hydrogen atom in its path to release its own faint signal in near-perfect unison, the radio equivalent of an entire choir finding the same note all at once after being struck by the same sudden gust of wind, each voice on its own too quiet to notice, all of them together suddenly loud enough to fill the whole room. The result would be a brief, narrow, startlingly bright pulse at exactly the hydrogen line, gone again almost as quickly as it appeared, indistinguishable to an instrument like Big Ear from precisely the kind of artificial signal the whole search had spent decades hoping to find. It is a genuinely elegant idea, explaining not just the signal's frequency and narrow width, but its single, unrepeated nature as well, since a trigger this rare, a magnetar outburst catching a hydrogen cloud at precisely the right moment and the right angle, might reasonably be expected to happen once, and then not again, for a very long time, if ever, from the same patch of sky. It is worth being plain about what this particular explanation would actually mean if it is eventually confirmed. It would not mean the signal came from anywhere artificial at all. It would mean the universe had, entirely by accident, produced a burst of natural radio energy so precisely shaped, so narrow, and so perfectly centered on the one frequency an entire field had spent decades watching, that it became, for 72 seconds, functionally indistinguishable from the very thing that search had been built to find, confirming that explanation beyond doubt would likely require catching another such flare in progress. And researchers involved in the project have continued combing through additional archived data and inviting outside volunteers to help comb through it as well, in the hope that a second example, anywhere in the historical record, might finally settle the question one way or the other. Mendez and his team were careful in presenting this idea not to claim they had solved anything. Their own published work described it not as an answer, so much as a sharper, more precise version of the same open question the field had been carrying since 1977. A candidate explanation grounded in real, observed data rather than pure speculation, but a candidate all the same, not yet a confirmed conclusion. There was a certain poignancy built into the project from the start. The archive data the team was combing through had been collected in the early months of 2020, only months before the enormous Arecibo dish itself, one of the largest and most storied radio telescopes ever built, suffered a catastrophic structural failure and collapsed entirely, ending decades of observations from that site for good. The instrument that gathered the very clues pointing toward the best explanation yet for the waterhole's oldest mystery no longer exists to keep looking, leaving the team to work forward from what had already been recorded, rather than gathering anything new from Arecibo itself. A refined version of their analysis, published roughly a year later, narrowed the likely origin point on the sky further still and nudged the estimated frequency slightly higher than the original 1977 measurement had suggested. The kind of small correction that ordinary scientific refinement produces once better instruments and more careful analysis are brought to bear on old data. It remains, as of this telling, the most scientifically grounded explanation anyone has offered for what Big Ear recorded that night, resting on an actual physical mechanism observed elsewhere in the data, rather than on comets that were never quite in the right place, or a star that stayed silent when astronomers finally checked. It is not proof. The team that proposed it has never claimed otherwise, and confirming it beyond doubt would likely require catching another such flare in the act, an event that, by its own proposed nature, might be rarer still than the original signal itself. One further, far more speculative thread entered the story only recently, in the autumn of 2025, and it deserves to be treated with considerably more caution than anything discussed so far. Earlier that year, astronomers had confirmed the arrival of only the third interstellar object ever detected passing through our solar system, a wandering comet given the designation 3I Atlas, following two previous visitors from beyond our own solar system detected in the years before it. An astrophysicist named Avi Loeb, working at Harvard, noted that this new visitor had arrived from a direction in the sky sitting unusually close to where the original signal seemed to have originated decades earlier, close enough that Loeb calculated the odds of that alignment happening purely by chance at well under 1%. He raised the possibility, publicly and quite openly speculatively, that the two might somehow be connected, though he offered no specific mechanism for how an interstellar object could have produced a radio transmission like the one Big Ear recorded, and he was careful to frame the observation as a curiosity worth investigating, rather than a claim he was prepared to stand behind. It is worth pausing on why a coincidence like that, however striking the arithmetic sounds, does not amount to evidence on its own, especially for an audience that has just spent this much time learning how carefully every other candidate in this same story was checked before being taken seriously. Unlikely alignments turn up constantly once you go looking for them across a large enough set of possibilities, the same way two strangers meeting at a party might discover they share a birthday and feel a brief jolt of astonishment, without that shared date implying any real connection between two lives that unfolded worlds apart. Radio telescopes that subsequently listened to 3I Atlas directly found only the ordinary chemical signatures expected from a natural, icy interstellar wanderer, nothing resembling a narrowband transmission of any kind. A striking coincidence of direction is not evidence of a connection, and a single researcher raising an intriguing question in public is not the same thing as a finding accepted by the wider community that studies these signals for a living. It belongs, for now, at the far speculative edge of this story, worth mentioning honestly rather than leaving out, but resting on nothing more solid than an angle in the sky and a probability calculation. What is left after comets that did not fit, a star that stayed quiet, a magnetic flare that fits better than anything else but still is not confirmed, and a coincidence of direction that so far has produced no supporting evidence at all, is very nearly what the case has always been. A single, extraordinary recording, matched to theory with remarkable precision, tested honestly against every explanation anyone has managed to propose, and still, after very nearly 50 years, without a confirmed answer either way. Consider what that list actually represents. 4 separate attempts, spread across nearly a decade by researchers working independently of one another, with no shared incentive to agree, arriving at 4 different conclusions. 2 explanations, checked carefully against the evidence and set aside. 1 candidate resting on real data and taken seriously by the field without yet being confirmed, and 1 speculative aside offered publicly but never seriously adopted by anyone beyond the researcher who raised it. That is not the pattern of a case nobody has bothered to examine. It is the pattern of a case examined about as thoroughly as the tools of each era allowed, repeatedly, by people with every professional incentive to find a tidy answer and move on to something else, none of whom ever quite managed it. A career is rarely built on confirming that a beloved old mystery remains, stubbornly, still a mystery. Each of these researchers had every reason to hope their own explanation would be the one that finally closed the file, and each, to their credit, reported honestly what the evidence actually showed instead. Big Ear is gone now, replaced by fairways and a well-kept green. Eamon, long since retired, has spent far more of his life being asked about those 6 characters than he ever spent reviewing the printout that produced them. The observatory in Puerto Rico that gathered the data behind the most promising current explanation collapsed entirely years ago and will never gather another reading. And still, after all of that, after every instrument involved in this story has either fallen silent or been replaced by something newer, the question those 6 characters first raised has outlived every telescope that has ever tried to answer it. What remains is not a mystery nobody has taken seriously. It is a mystery that has been taken as seriously as science knows how to take anything for very nearly 50 years running, without ever once being allowed to harden into either a confirmed discovery or a settled dismissal. What that particular kind of open question asks of the people still carrying it is where this story turns next. An open question like this one asks something quiet of the people who carry it, something closer to patience than to hope. Most mysteries, given enough time, resolve in one of 2 ordinary ways, and it is worth being specific about what those 2 ways actually look like before considering how rarely anything manages to avoid them both. Either the evidence eventually arrives and settles the matter, or the question simply stops being asked, fading out of the conversation, not because it was answered, but because everyone interested in it eventually moved on or passed on themselves. A letter gets answered, or it goes unanswered long enough that whoever sent it stops checking the mailbox. A missing person is found, safe or otherwise, or else a search is eventually stood down and a family learns, slowly, to speak of someone in the past tense. Very few questions manage to do neither. Very few stay exactly as open and exactly as urgent, nearly 50 years after they were first raised, still checked, still argued over, still worth an honest researcher's career to investigate carefully rather than dismiss. Whatever else can be said about those 6 characters circled in red ink, They have never once been allowed to fade quietly into the second category, and they have never once earned their way into the first. There is a particular kind of discipline required to keep a question open that long, without either forcing an answer onto it or simply giving up. It would have been easy, at almost any point over the last several decades, to declare the matter settled, either by embracing the most exciting available explanation and calling it proof, or by seizing on the first plausible-sounding mundane answer and closing the file for good. It would have been easy in the other direction too, simply to stop mentioning it, to let it drift into the same drawer where 1,000 other unverified claims eventually end up filed away and quietly ignored, brought out only for anniversary articles. Nobody reads closely. Neither happened. Instead, one researcher after another kept doing the harder, less satisfying thing, taking the case seriously enough to test, rigorously enough to fail honestly when the evidence did not support the answer they were hoping for, and humble enough to say so plainly, rather than quietly burying a disappointing result in a footnote nobody would ever find. That is not the behavior of a field chasing a fantasy. It is the behavior of a field that has decided a genuine question deserves to be treated as one, for as long as it takes, even when as long as it takes turns out to mean nearly half a century, with nothing to show for it but a longer and more carefully tested list of things it probably was not. Somewhere in that list of careful, honest failures sits a man who spent one ordinary afternoon doing routine, unpaid work, and ended up spending the rest of his life fielding the same question from strangers, in a way no one could have predicted for him on any of the ordinary mornings that came before it. He did not set out to become the person forever associated with 6 characters and a single word written in the margin of a printout. He set out, like every other volunteer at that observatory, simply to read the page in front of him as carefully as he could, on a day that felt, by every outward measure, exactly like the many ordinary days that had come before it. What followed was never entirely his to control. Once a discovery like that leaves a person's hands, it stops belonging only to them. It becomes public property in a way few private moments ever do, picked over by strangers, argued about in places its original observer will never visit, attached permanently to a name that might otherwise have lived a perfectly ordinary, private scientific life, teaching classes, publishing modest papers, retiring quietly the way most careers in science eventually do. Instead, that one afternoon followed him everywhere afterward, into every interview, every anniversary article, every fresh wave of renewed public interest whenever a new candidate explanation made the news. There is something worth sitting with in that alone, apart from anything the signal itself may or may not have been, the particular, permanent weight of being the one person present when something inexplicable happened, and having to carry that presence for the rest of your days, answering the same handful of questions again and again for people who were not yet born the night it happened, whether you ever wanted the job or not. By every account he ever gave of it, he carried that weight with an unusual amount of grace, never overselling what he had seen, never trading the strength of his own credibility for a louder headline, offering the same careful, hedged, honest account decades later that he had offered from the very beginning. Widen the lens far enough, and this single case becomes one small chapter inside a much longer, much stranger undertaking, one that began quietly in a physics journal and has never really stopped since, even during the years when almost no one outside the field was paying attention. The search for a genuine signal from beyond this solar system has now been running, in one form or another, for well over 60 years, ever since 2 physicists first worked out, on paper, where such a signal would most likely be found if it existed at all. It has survived changes in government funding, changes in the instruments available to conduct it, and generational turnover among the researchers carrying it forward. Each new group inheriting the same open question from the last, and adding whatever small refinement their own era's technology allowed. In all that time, across every instrument built specifically for this purpose, across radio telescopes on nearly every continent, and, eventually, listening programs backed by fortunes no observatory in 1959 could have imagined, not one confirmed transmission from another civilization has ever been recorded. Not one. This single, unrepeated night in 1977 remains the closest anyone has come, and even it, after everything, remains unconfirmed. Measured against the length of a human life, 60 years already feels like a great deal of patience to ask of anyone. Measured against the age of the stars this search is aimed at, some of them far older than the planet. Doing the listening, it barely registers as a heartbeat. Judged purely by results, it would be easy to call the entire enterprise a failure. 60 years and more of careful, expensive listening producing nothing anyone can point to and call proof. Consider what it means, practically, for a researcher entering this field today. Nobody currently working on this question was alive when Cocconi and Morrison first proposed listening at the hydrogen line, and the youngest of them were not yet born when Eman circled those 6 characters in red ink. They inherited this particular question the way a person inherits a family trade or an unfinished piece of land, learning its history secondhand, absorbing decades of careful, disappointing groundwork before ever getting the chance to add anything of their own. And they took it up anyway, fully aware that the search had already run longer than most careers last, with no particular reason to expect their own contribution would be the one that finally settled it. That is a strange thing to choose, when so many other, faster-moving corners of science offer a person the chance to see their own questions answered within a working lifetime. It says something about the pull of this particular question that it keeps finding new people willing to take up watch anyway, signing on for a shift with no fixed end and no guarantee anyone will ever relieve them of it with an answer. Some of those people are not professional astronomers at all, but ordinary volunteers combing through archived data in their own spare time, continuing, whether they think of it this way or not. The exact same tradition Eman and his colleagues began in that Ohio cornfield, unpaid, unhurried, and entirely willing to find nothing, again and again, for the sake of the one time they might not. That judgment misunderstands what the search was ever actually attempting to measure. No responsible scientist involved in it, from the very first proposal onward, ever promised a timeline, and none pretended the search would be quick simply because the reasoning behind it was sound. The honest version of the proposal was never "we will find something." It was only "this is worth looking for, and here is a sound, physically grounded reason to believe we might know where to start." A search built on that kind of honesty does not fail simply because it has not yet succeeded. It only fails if the people conducting it stop looking carefully, start pretending weak evidence is strong evidence, or quietly abandon the standards that made the search credible in the first place. By that measure, the record is a good deal more impressive than a simple count of confirmed discoveries would suggest. Every candidate explanation raised for this one signal was tested against real evidence rather than accepted on the strength of how satisfying it would feel to believe. Every dead end was reported as a dead end rather than dressed up as something more, even when reporting it that way meant disappointing an audience that clearly wanted a cleaner story. Imagine, for a moment, how easily this particular case could have gone differently. A less careful field might have announced the comet explanation as settled fact the moment it was proposed, simply because it offered a tidy, ordinary answer, and most people are relieved to have a mystery closed. A less honest one might have quietly buried the fact that the leading candidate star turned out to be silent, rather than publish a negative result nobody enjoys reporting. A less patient one might have stopped listening decades ago, once it became clear that a quick answer was never coming. None of that happened here. The case survived exactly because enough people, across enough decades, refused to take the easier path at every single one of those forks, choosing instead the slower, less dramatic work of simply telling the truth about what the evidence did and did not show. There is a version of this story that spends all its attention on what might be out there, and very little on what the search itself says about the species doing the searching, and that imbalance is worth correcting before this account closes. A civilization does not fund an effort like this one, does not send volunteers out to a cornfield year after year for no pay, does not train new researchers to inherit a question they will likely never see answered, unless something in that civilization values the asking nearly as much as it would value an answer. Nobody has ever been required to search for this. No harvest depends on it. No illness is cured by it. No practical advantage accrues to a species that spends decades listening patiently to empty static, on the off chance that, once, it was not entirely empty, and yet the effort was made regardless, year after year, by people with better things they could have been doing with their evenings. And yet, the listening continued anyway, funded, staffed, and defended by people who understood perfectly well how unlikely success was and chose to keep at it regardless. There is a certain rightness in the fact that the specific stretch of sky this species chose to watch most closely was named, decades ago, after a gathering place, a spot in open country where different creatures set aside their differences long enough to share what they needed most. Whether or not anything else has ever actually gathered there alongside us, humanity has spent well over half a century proving it was willing to show up. Whatever else this particular case does or does not eventually reveal about the wider universe, it has already revealed something quietly remarkable about this one, small, curious species doing the listening. Consider, for a moment, just how much of the sky and the radio spectrum remains, even now, essentially unexamined. A radio receiver can only listen to one narrow slice of the dial at any given moment, the way an old car radio can only play one station at a time, no matter how many others are quietly broadcasting up and down the band around it. Even the most ambitious modern search programs, built with vastly more capability than Big Ear ever had, can only aim at a limited number of stars for a limited number of hours, tuned to a limited range of frequencies, out of a sky containing hundreds of billions of stars in this galaxy alone, and a spectrum stretching far beyond the narrow waterhole. This particular story has centered on. Some of the most capable searchers running today can scan through many stars in a single sitting, examining each one for only a few minutes before moving on to the next, which sounds thorough, until it is measured against a galaxy old enough and vast enough to make even a few thousand stars feel like a single handful of sand lifted from a beach that stretches farther than anyone has ever managed to walk. Every deliberate search ever conducted, added together across more than 60 years, has still sampled only the smallest fraction of everywhere a signal could plausibly be hiding. Silence, under those conditions, was never strong evidence of absence. It was only ever evidence that nobody happened to be listening to the right channel at the right moment, pointed in the right direction, which is a very different and far less final kind of silence than it first appears to be. There is a second scale worth holding alongside that one, measured not in distance but in time. Whatever actually produced that 72 seconds of narrowband energy, positioned somewhere out along that same stretch of sky towards Sagittarius, was almost certainly a great many hundreds, and quite possibly several thousand light-years distant, which means the energy Big Ear picked up that August had already been crossing the emptiness between the stars for longer than human beings have kept written records of their own history. Whatever moment caused it to begin its journey, human civilization had not yet learned to write when it started. Entire empires rose and fell somewhere on this planet, while that single burst of energy was still crossing the gap. It arrived, at last, at the one particular moment in all of human history when a receiver built specifically to notice exactly that kind of signal happened to be listening, aimed at exactly the right patch of sky, tuned to exactly the right sliver of the dial. Whether or not it ever meant anything, the timing alone is difficult to sit with for very long without a certain quiet vertigo. Sit with that thought long enough, and something quietly unsettling follows from it. If the signal recorded that August night truly did come from somewhere else, somewhere with its own sky and its own patient watchers, then whatever sent it may well have gone on sending, or may be sending again this very night, on some frequency nobody currently has a receiver tuned to, from some direction no telescope happens to be pointed toward at this particular hour. Somewhere, above the roof of whatever room this is being heard in, that same stretch of sky is turning slowly overhead right now, carrying whatever it carries, indifferent to whether anyone happens to be listening. Or it may never happen again at all, gone as completely and as permanently as a single spark that flew up once from a fire and went dark somewhere overhead before it ever reached the ground, a one-time event with no cause anyone will ever get to examine up close. What would actually resolve this, one way or the other, is not a mystery in itself. A second confirmed flare from a cold hydrogen cloud, caught clearly enough to match against the archived reading in every detail, would go a long way towards settling the case in favor of the natural explanation. A second narrowband transmission, repeating from the same coordinates under controlled, verified observation, would settle it just as firmly in the other direction. Neither has happened yet. Both remain, in principle, within reach of instruments already listening tonight. The case is not stalled for lack of a plan. It is simply waiting on an event that, by its own nature, cannot be scheduled, requested, or hurried along by wanting it badly enough. There is an old habit in certain households of leaving a porch light burning after dark, not because anyone is expected that particular night, but because someone might be, and because leaving it dark on the one night it mattered would be a harder thing to live with than leaving it lit on all the ordinary nights when nobody came. Nobody keeps a running tally of every night the light burned for no reason. The cost of that habit is small and easily forgotten, spread out quietly across years of ordinary evenings, while the value of it, on the one night it might actually matter, is almost impossible to measure in advance. Radio astronomy has kept a version of that same porch light burning for well over half a century now, aimed not at a road, but at an entire sky, not for one guest, but for the faint chance of any answer at all. From any direction, on any given night, it has stayed lit through decades, in which nothing at all walked up the path. It stayed lit through one single night, when something, briefly, unmistakably, seemed to. None of this requires a tidy resolution to matter. That may be the hardest part of this particular story to sit with, and also the most honest. The temptation in telling it is to reach for something more satisfying at the end, a final piece of evidence, a confident verdict, a sense that all this careful looking was leading somewhere definite. It was not, and pretending otherwise would betray everything that actually makes this account worth telling in the first place. A storyteller could easily choose the most exciting candidate explanation, present it as though the matter were essentially closed, and let the audience walk away with the satisfying but false sense that the mystery has been solved. That would be a kinder ending in some ways, and certainly an easier one. It would also be a lie, dressed up as a bow tied neatly around a story that has never once, in nearly 50 years, allowed anyone an honest bow to tie. This account has tried, throughout, to resist that particular temptation, naming each candidate explanation exactly as strongly or as weakly as the evidence for it actually warranted, and it would be a strange kind of betrayal to abandon that same discipline in its final moments, simply because an ending demands one. The real achievement here was never going to be solving the case. It was always going to be this: an entire field of careful people faced with something genuinely strange, refusing every convenient shortcut to certainty, refusing to call a candidate explanation a confirmed one, refusing to let a single researcher's speculation stand in for the community's actual judgment, and refusing just as firmly to let the whole question quietly disappear simply because it had grown inconvenient to keep answering. Holding a question open honestly for very nearly 50 years, without flinching toward a false yes or a lazy no, is a rarer discipline than it sounds, and it is, in its own quiet way, exactly the kind of achievement that rarely gets its own headline. Certainty is easy to manufacture and hard to walk back once it turns out to be wrong. Honest uncertainty, held that steadily for that long, is a far more difficult thing to sustain and a far more trustworthy one to inherit. If nothing else about this story survives in memory, that distinction is the one worth keeping. The actual page still exists. The original printout, the red circle, the single word written almost without thinking in the margin beside it, is kept today in a public historical collection in Ohio, available for anyone with a genuine reason to see it in person. It is, by now, simply an old piece of paper, its ink faded, its edges worn the way any decades-old document eventually wears, filed alongside countless other artifacts of the state's history that have nothing to do with the search for other civilizations. There is something fitting in that ordinariness. The object at the center of the most carefully studied unexplained signal in the history of the search for company in the dark is not kept behind reinforced glass in some grand hall built to inspire awe. It sits in a filing box, one historical document among many, waiting patiently, the same way the question it represents has waited for as long as it takes. What remains, then, is not an unsolved case waiting for someone to finally crack it. It is a question that has been asked as carefully and as honestly as any question in modern science, for as long as anyone has known to ask it, and that continues to be asked in exactly that spirit tonight, by researchers who may never live to see it answered and who keep asking anyway. There is no way to know, from here, whether that patience will ever be rewarded, whether some future night will finally bring a second reading to sit beside the first, or whether the case will simply continue exactly as it is now, indefinitely, an open question quietly handed down from one generation of careful listeners to the next, the way this account itself has just handed it to whoever is hearing it tonight. Both outcomes are possible. Neither has arrived yet, and neither is owed to anyone simply because the waiting has already gone on so long. Somewhere, a receiver not so different in spirit from the one that once stood in that Ohio cornfield is still tuned to a narrow, quiet stretch of the dial, still listening, still patient, still willing to wait for something that may never come again, because the only alternative to that particular patience is to stop listening altogether and nobody who has followed this story this closely has ever quite been willing to do that. That is where the story actually rests tonight. Not on a discovery, and not on a dismissal, but on the plain, settled fact of an old question, asked honestly, still open, still being tended by people who understand exactly how unlikely it is that they, personally, will ever see it closed, and who show up to listen again anyway. Drift off now. Somewhere overhead, the sky is still, quietly listening